Okay, so now recording. If I do forget, could someone just please remind me to post the attendance code at some point during the lecture? Okay, so basically, so as far as I know, this is where you guys finished with Prof. Kulto on Tuesday. So I'll basically continue from here. Okay, so we are basically like still doing file handling. And then so in this slide, like you guys were looking at IO manipulators, for example, for like adding like certain like formatting options in your stream. Let's say, for example, an output stream when you're outputting data and so forth. Okay, and then so the next slide basically focuses on further stream usage or covers further stream usage. And then so like another way to use streams, for example, is to pass streams as parameters to functions. So for example, this is a function called copy file, and then we are passing a stream, which is an input file stream. We're passing it by reference. This is important when dealing with file streams because remember that like you don't want to create a copy, of the file stream and then modify that copy and then destroy the copy, like when you reach the end of this function, right? Because then it won't actually modify the stream that you passed as a parameter, right? You want to keep modifying the same stream so that whatever you do with the stream inside of the function is actually done to the original stream that you passed as a parameter. So that's why you pass it by reference. And then, that's an output file stream. And then another thing we can do with streams is that, for example, we can do this sort of check, like when we're reading from a file stream and extracting the data from the stream into a variable. And then we can actually put this in a while loop, right? So what we're basically doing is we're using the truth value of the extraction operators. In this case, it's the extraction operator. We're using the truth value of the extraction operator's return value to test for the end of a file, right? So this is very interesting, and it actually makes your code much more compact, right? So instead of having to first check if there's something in the stream and then read from the stream, you can just combine the check and the reading in one line and just put that in a while loop. And then this will ensure that, if the check for contents in the stream returns false, then you won't read into the variable, but instead you will just terminate this cycle or this loop. So how is this possible? This is possible because, so obviously you have the overloaded version of this operator. That is why you are able to do this. And then there's also a function that can convert the return stream reference into a Boolean value based on whether the data can be extracted from the stream, right? So you also have a function that checks if there's still content or if data can still be extracted from the stream. And then if that function returns false, then the while loop basically terminates. Okay, so so far we've been looking at sequential text files, and basically that was also the content of the tutorials this week. But there are cases where you want, for example, to read data in a file and not necessarily start from the beginning of the file, right? So far, what we've been looking at is opening a file and then reading the file from the start and then all the way, for example, up until the end of the file. We didn't have to read the file all the way until the end, but the point is we always had to start at the beginning. So sometimes that's not the case. That's not always the case with files. Sometimes you want to open a file and then you want to start reading it, let's say, from a particular position. And then so that is where the idea of random access files comes in. So with random access files, we are trying to give ourselves the option of choosing how we want to read the file and from where we want to read it. But so C++ makes no distinction between sequential, which is what we have been doing so far, and random access files, right? So all files are basically treated as streams of characters, right? So C++ doesn't differentiate between sequential access and random access, right? It just treats a file as a stream of characters, and then we have to use certain functionality that comes with stream objects to actually achieve random access, right? So by extension or by definition, right, technically speaking, all read and write in C++ are sequential, right? But we are going to find ways to achieve random file access, right? So obviously, then random access can be much faster than having to sequentially retrieve each record. Imagine if you're reading a huge like chunk of records, and then you have to literally, go through each record until you got to the record that you wanted. Instead of having to waste all like that time, like basically like reading each and every record until you get to where you want, you could just skip, like in a song, or if you're watching a YouTube video, right? You can just move the seek to where you want to start streaming the video, and then you can just start streaming from there, right? So you can just start watching from there. So that's the whole point with random file access. And truly, strictly speaking, C++ actually has like a seek in the form of a pointer, right? It's called a seek. So for example, this function is when you're trying to get the position of the seek, and this is where you're trying to place the seek like at a certain point in the file. And then another thing you can do is you can call the tellg function, which actually tells you where the current seek is, right? And remember, so seek is a pointer, right? So this actually just tells you the current byte position in the file. Okay, so and then so let's look at an example of random access files. So in order to move to the beginning of a file, right? So then we can use this get function, right? Which tells us the current position of the seek, right? So then, like in this case, then we can basically, oh no, yeah. So actually, yeah. Okay, so there's actually two kinds of pointers. Yeah, so I actually confuse this with the tellg function, right? So there's something called the seek pointer, and then there's something called the put pointer, right? So the seek pointer is for reading, and then the put pointer is for writing, right? Yeah, and then so this function basically moves the get like pointer, which is the seek g, also called seek g. So it basically moves it to, for example, like a particular position in the file, right? And this is so your program will use this pointer to read from the file. This is when you're reading from a file, right? And then it will use the put pointer, right? And then to move the pointer that your program uses to write into the file, it will move it to a particular position in the file. Yeah, so that's the correct definition. Okay, and then the tellg just tells you where you are currently in the file, right? So it tells you, for example, where the get pointer is in the file. Okay, so now let's say we want to read from a file, and then so we use the get, we want to check where the get pointer is. Actually, we want to move the get pointer. Why do I keep saying check? Okay, but in any case, so now basically then that's what we're doing. We're seeking the get pointer to a particular position in the file, right? So we use seek g. So in this case, when we are seeking 0 bytes from the beginning of the file, what we're basically doing is we are reading from the start of the file, right? Which is the same with sequential file access, right? What we have been doing so far, right? We've been reading files from the top or from the beginning. So that is the same thing that's happening here. This is going to achieve the same effect. We are just moving 0 bytes from the beginning of the file. And then if we want to move to the end of the file, then we move the pointer 0 bytes from the end of the file, right? Yeah, so that's the logic. And then if we want to move, for example, a certain number of bytes away from the current position in the file, then we call the seekg function. And then we tell it the number of bytes that we want to move. And then we basically tell it that we want to move these number of bytes from the current position in the file. Okay, so in terms of designing a file format, so in order for us to achieve our goal of non-sequential file access, we need to constrain ourselves to reading and writing in fixed size increments, right? So this is important, right? Because let's say, for example, you have a text file. Let's actually just have an example of this. Just open this quickly. Please just give me a moment. Okay, so let's say you have a text file, and then let's say here you have data like, for example, let's actually do this, 3, 4, 5, right? So with random access, right, we want to be able to move through the file in fixed size increments, right? So we want to be able, for example, to say, I want to move to position 3, right? And then we should be able to move like 1, 2, 3, right? And be there, right? Or if I want to move to position 5, I want to move there, right? But you probably can already see how this could be a problem. For example, with what we have here, right? If you look at 3, for example, the string 3, it has 5 characters, right? Whereas the string 2 has 3 characters, right? So that's the problem, because I can't just use indexing, like as we know it. I can't just say I want to move to index 4, you know, in the file, because it doesn't mean that it will move me at the start of the string, right? Because how many bytes is it to get to index 4? It's, remember, a character is 1 byte in C++, so 1 byte is allocated for a character. So then it would move 1, 2, 3, and then there's also the end of line character, so that's 4, and then 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14. So I actually need to move 14 bytes in order to get to this position in the file, right? Including end of line characters, right? So that means another alternative would be then to assume that each line was a certain number of bytes, right? But then that's still a problem, because if I assume that this is, for example, 3 bytes or 4 bytes, then if I say move 4 bytes, then fine, it will move to the beginning of the string. And then if I say move a further 4 bytes, then it won't, oh yeah, it will move to the beginning of the string. But then if I say move another 4 bytes, it won't move to the beginning of this string, right? What it will actually do is it will say 1, 2, 3, 4, and then I'm stuck here, right? So then that would cause, let's say I wanted to write something here, then it would actually ruin my file, whereas let's say I wanted to actually put the, I don't know, like the string here or something like that, and then put an end of line character, right? But then I would have something like that, which is not what I'm looking for, right? So then we want to be able to move in fixed size increments, right? So that's the aim. We want to be able to move in fixed size increments. So that's the whole idea that we are trying to get to, or the whole goal, like that's our goal. All right, so then we can move read-write pointers to an appropriate index in the file and retrieve only the record we're interested in. But so, even if, let's say, we're not writing textual data, right, which is text, let's say we're writing binary data where we could actually write, you know, actual integers and doubles and floats and strings and characters into files, we have to account for the fact that these have different sizes, right? So we need to find a way for us to be able to move in equal size increments. Okay, so what we will do is, so we'll actually get into that later in how we can achieve that. But so when writing to disk, we want to write, in order to write to disk, we will have to use the following functions. So these are the functions we have, right? So whether or not we're writing textual data or binary data, like we're going to use these functions. So with textual data, actually, you can also use the stream insertion operator to write. You can use the stream extraction operator to read, right? But with binary data, we are going to have to use these functions, which is write and read, right? And then you'll realize here that when we're writing to a file, even though, let's say we want to write an int, right? Or like a struct, for example, to a file, we are going to have to convert it back to a char pointer, right? Remember, a string in C++ is an array of characters. So then we will convert it back to a char pointer. And then we'll specify the size like of each entry, like as we write, right? If there's many elements, then we'll specify the size of the entry that we're trying to write, right? And then we'll specify, and then we'll provide the string representation of that element. Okay, so you can't always read the string representation. I think I did show this to you guys like during my tutorial, if you attended my tutorial. But for example, let's say we have an example here, and then you want to read like a binary file. An exe file is a binary file. It's an example of a binary file. So if you wanted to read this, right, and then you opened it in a text editor, right, this is what you'll see, right? This is not human readable text, right? It's gibberish in the human eye, but it's still a textual representation of the data in the file, right? So this is what it means, right? So you convert the file into an array of characters, even though you most of the time you wouldn't be able to make sense of that data. Okay, and then so we are going to use the f stream object, file stream, instead of the f stream and the off stream that we've been using. We'll just use the file stream, and then it contains both methods, right? So we can use it to write and we can use it to read. And it's also important to note that when you're reading, you also specify the size of each, you know, data, you know, like each chunk of data that you're reading, right? You'll specify the size. So then, I already mentioned this. Note that the first parameter is of type char pointer, which is consistent with how C++ treats files as character sequences, right? So there's no difference, for example, between like a text file or a binary file, right? There's no fundamental difference between those in C++, right? It treats all of them as sequences of characters, right? So we will have to make a cast to a char pointer in order to write data of a different type. Okay, so let's get to data structure, padding, and byte alignment. Okay, before we get to here, let me just check if there's questions. So the number of bytes are in bits or integer. Do you say n is 4 or n is 100? Okay, I'm not sure if I understand what you mean, but so remember when you create an integer, for example, when you create an integer like this in your program, right, int a, right, you are asking your compiler to allocate 4 bytes of memory, like in your, for example, like in your RAM, right? That's what you're doing. You are asking for 4 bytes of memory to be allocated for this variable, right? So when you create a char, A or I don't know B, then you're asking your compiler to allocate 1 byte of memory, right? If you're creating a char array, for example, that has 6, that can store 6 characters, then you're asking your compiler to allocate 6 bytes in memory for your array. So that's essentially what you're doing. Okay, so can we put something like a hash to know the end of line? Well, you can do it, for example, if you want, you know, like like to place specific markers like in your text file, you know, to do like a check, for example, like an if statement to know that you've reached the end of the line. But it's not necessary in C++ because if you use, for example, the stream extraction operator, when it reaches the end of the line, it will stop like writing into that variable, or like extracting into that variable, and then like it, or rather it'll stop extracting that string, right, for that particular statement, right? And then let's say, for example, that you're using a loop, right? Like each end of line character, like the stream extraction operator will, when it reaches the end of line character, it'll stop extracting, right? And then when the loop begins, then only then will it read the next piece of data, right? So you don't have to do that in C++. Okay. So .exe is the extension of a binary file. No, a binary file does not have to have the .exe extension. A binary file is a binary file because of the contents of the file, right? So it can have any extension. What matters is the contents that are inside of the file, right? So it so happens that files with the .exe extension are almost all the time binary files. Again, so yes, so exe is one common example. You could use any extension. Okay, so yeah, so for example, I could create a text file and give it the extension .exe, but store textual data inside of it. And then if I open it using a text editor, right, I'll see text. I won't see gibberish. Okay, so yeah, so for the sake of efficient reading and writing in C++, or C++ will by default try to ensure that certain data members have a particular byte alignment, right? So they start on a certain memory address that is an exact multiple of a number of bytes, depending on the data type of that member. So the compilation, also the compilation settings, and whether the operating system is 16 bits, 32 bits, or 64 bits, right? So, and this actually does consume more memory than required for your data. So like, for example, let's actually do an example of this. Let's see if we can try and get this to happen during this session. So, but basically the idea is that if, for example, you create a struct in C++, let me just open my example project. Okay, so let's say, for example, if you create a struct in C++, so let's create a struct. And then let's say example struct. And then let's say, for example, or let's say this stores information about say student. So then let's say we have an int, which is the student's age. We have a char. Let's say this is the student's gender. And then we have a double, which is the student's final mark, right? Okay, so we know that an int is 4 bytes. Right? And then we know that a char is 1 byte. And then we know that the final mark is, so a double in C++ is 8 bytes, if I remember correctly. So then if we create like, for example, so if we want to know the size of the struct, we can use the size of function, and then we can just say student, right? So what is the size of student, right? And then let's output let's see what the output is. Okay, so it says 16, right? So let's check. Let's actually count for ourselves. So 8 plus 1, that's 9, plus 4, that's 13, right? So that's a huge discrepancy, right? So this should be 13, not 16, right? And this is what C++ will do when, for example, you create a struct. And it does this because it wants to be able to store, for example, your struct, or it wants to be able to allocate memory for your struct in such a way that it is like a number that is to the power of 2, for example, right? So like, or it's a multiple of a certain number of bytes, right? So in this case, for example, it wanted to make sure that that number was 16, right? So usually the number will be a power of 2, right? So it will be like 8 or 4 or 16 or 32 or 64 or 128 and so forth, right? Or it will try to make it like a multiple of a number of bytes, right? And that is exactly what it did here, right? The size of the struct is 13 bytes, but it actually padded the size, using extra memory, that actually will not be used for anything, just so that the size of the struct is, for example, like to the power of 2, right? And then so in order to save memory, right, we want to actually remove that, right? And then we can control this behavior by like this following mechanism, right? So basically what we can do is we can use the pragma directive, right? So this is a preprocessor directive. It doesn't really get compiled with your code. Just tells the preprocessor how like your compiler should allocate memory, for example, this data type, this particular struct, right? So then we create the struct, and then we use the pragma directive. So the first statement is the pack push, where what we're basically doing is we are saving the current alignment settings, right? So we're basically pushing these settings onto the stack, right? Remember, a struct, for example, like this, like for example, if it's not a pointer, right, then your compiler will allocate memory for it on the stack, right? So then what we're trying to do here is we are trying to push these settings onto the stack, and then we are setting the alignment, right? So you can, for example, make this 2 or like 4 or something, but so the setting that we are going to use is 1, right? So 1 basically means no padding, right? So if you use something like 2, for example, like it does padding for some of the like the variables, and then not some, and so forth. There are different like kinds of settings. But then if we want to remove the padding altogether, then we set the alignment to 1, right? And then after setting the alignment to 1, then what we do is then we basically pop, which means so then this basically just deletes the setting after the declaration, right? Because that's what we want to do. We want to push the settings, set the setting, make the declaration, so allocate the memory for, and then we want to delete the settings so that they are not there on the stack when we do more declarations like of other data types, right? We want these settings to only exist for the struct, and then we want to delete them after we've allocated memory for the struct. Okay, so then let's try that out. So pragma pack push, and then now let's set the alignment settings to 1. And then delete the settings or undo the alignment settings. So now let's see what the size of the struct will be. So hopefully it will be the correct number, which is 13. Yeah, so that is correct. So as you can see, the size of the struct is no longer 16, which was a bit wasteful because it used 3 extra bytes, which will be ignored like during the execution of the program, which is kind of wasteful. And then now our struct only uses the memory that it needs, right? Which is 13 bytes. Okay, so that's the whole idea. Yeah, so before I continue, let me just check for more questions. Okay, so unless we use pragma, we'll constantly need to be rounding up to when accessing our files. Yes, so basically, unless we use these alignment settings, our compiler will always include this padding, right? So we're trying to avoid this padding so we don't use like this extra like allocated memory that is ignored. So setting the alignment to 1. So as I did mention, we are basically so like the basic definition of it is that you are not including any kind of padding, right? So when you, for example, use 2 or like 4 and so forth, so your compiler will like pad like the memory, like the allocated memory, like in certain different ways, depending on the programmer's like desires, right? So what we want is we want to remove the padding altogether. So by setting it to 1, we're basically not including the padding. Okay, so what if you put 2 instead of 1? What would the size be? Okay, so yeah, it's been a while since I've played around with this, but I think this also like specifies how the padding should happen according to like the power of the number that you are putting here. If I'm not mistaken, I stand to be corrected with regards to that. It's been a while since I actually tried that out, right? So in this case, for example, if you put 2, what should happen, right, as far as I remember, is that it should then try to make the size a power of 2, right? So let's actually try it out. Okay, well, it didn't actually do that. I think it makes it a multiple of 2. Yeah, so it probably just added, because it was 13, probably made this 2 bytes. So it made the size of everything here a multiple of 2. Let's make it 4. Let's see what that does. Okay, so it makes it 16, which is a multiple of 4. Okay, so that's consistent with our assumptions. So you also can play around with it at your own time. But basically, we will just be using 1, which just means no padding, right? And then, yeah, because we're trying to eliminate padding. Can all these concepts be used to read and write on a file format like Excel spreadsheet? Will that be a different story? Okay, well, I think that would be like different because you'd be creating like an, like an Excel workbook. So like there'd be different, like rules that would apply to that. But this is just for writing like, like data, like for example, like data types, right? Complex data types. Like for example, with a struct, if we want to group data together, then obviously this is not like a primitive type where like it's just an int or a char or something like that. We want to group data together and then want to write it into a binary file, right? So then in this case, right, we know that our compiler will do some padding, and then we want to write that into the binary file, or want to write it in like we want to eliminate padding so that, and then you'll see why we are doing this as you continue. In the exam, can they ask you which mechanism we can use to control the size of the struct? Okay, so yes, so you should expect any kind of question based on the content that we're covering, right? So you could be asked, how can we align the bytes, or how can we control, how the compiler, allocates memory for a struct. Then you would specify that we can use this preprocessor directive. the pragma directive, and then if we want to have no padding at all, we can just use the 1 as our alignment setting. Okay, so in terms of writing to disk and some useful algorithms, so providing that our structs are not of a variable length, we can write them to disk by means of the following, right? So this is assuming that all of our structs, for example, will be like of the size, right? For example, if I create a struct called students and then it has this size, then I can write them to disk by means of the following, right? So then I can use this write function, and then I can then, remember we have to cast this to a char pointer, right, which is an array of characters. So then we can use the reinterpret cast, and then we can then provide the memory address of the struct, and then that should cast it to us, cast it for us to a char pointer. And then we remember for this function, you also have to specify the number of bytes. And then we know what the number of bytes are, right? It's the size of the type, right? So in this case, it's record type. In our case, it would be students. Okay, so we can also move to a particular record in a data file by way of the following, right? So if we want to write, remember, we need to move the put pointer, right? So we use seek, the seek put, and then function. And then remember, we have to specify the number of bytes, and then we have to specify where, like from which position in the file, right? Remember, we can use begin, we can use end, we also can use CUR, which is current, right? So then here, for example, we can move, let's say this is 10, then that's just my index, right? So this is how I can do indexing, right? So this is just a clever way to index, like your file, right? So that you can actually move to different positions, right? So then I can say, for example, I want to move to 10, so then that would just be 10 times the size of my struct. So in this case, it's 13, right? So that would be 13. So then that would equal to 130 bytes into my file, which would lead to the 10th record structure, right? So that's the whole idea, right? So this is how I can do my indexing. And then, so this is basically from the beginning of the file. Okay. And then, so we can also find the size of a data file in bytes and in terms of the number of records, right? Because we've established our mechanism for doing indexing, right? So then, for example, we can say, so define an integer that specifies the size in bytes, and then we can say move 0 bytes to the end of the file, and then file, so the size of the file in bytes would be then found by calling the tellg function, which will tell us how many bytes we are into the file, right? That's what we want to do. We move the get pointer to the end of the file, and then we just ask, where is the get pointer, right? And then that will tell us how many bytes into the file we are, right? And then if we want to know the index, right? So which record are we looking at, right? Is it the 10th record? Is it the 5th record? Is it the 20th record? Then we can basically just take the size, right? So in our case, if we had 10 records, so remember, our struct is 13 bytes long. And then if we have 10 records, then that would mean that our file size would be 130 bytes, right? So then if I move to the end of the file, then size in bytes would be 130 because our file is 130 bytes long. Then if I want to know how many records are in the file, I'll just divide 130 by the size of each record, right, which is 13, right? And then that would tell me that, so this would be the number of records. So it would be basically size in bytes divided by 13, right, which is the size of a student record, right? And then, so then that would be that. So that's how I know how many records are in the file. And then that's pretty much it with random access files. Okay, we're almost out of time, so this is definitely a good point to end the, or to stop. So I'll just stop here. And then, yeah, but that's it with, you know, like binary files and random access, right? So that's all there is to it, right? If you know how to do your, you know, alignment, to, you know, and then settings, and then you know how to write, you know, which is pretty straightforward. I mean, there's really nothing to this. And then you just providing the address of the, you know, the record that you're trying to write, and then you provide the size of a record, converting that to a child pointer, and then by reading, you just specify the position. If it's position 1, then you would provide a 1. That would be 1 times the size of a struct, which would be 13 bytes, which means that that would be the second record, right? So if you want the first one, then you would move to position 0. So it would be 0 times 13, which would be position 0. So you would read the first record, right? So if you want to read record 5, then you would do the same thing, right? Oh yeah, so obviously if you use 10 here, then it wouldn't be the 10th record, it will be the 11th record that you want to read, right? So pretty straightforward, nothing complicated. And then, so that's for reading and writing. And then if you want to check the number of bytes, then you use tell-g after moving the get pointer to the end of the file. And then if you want to know how many records are there, then you just divide the size of the file by the size of each record. And then that's that. And then let's look at questions. So after here, we'll be looking at like files for logic, so reusable software components. And then we'll specifically be looking at DLLs, so dynamically linked libraries. Thank you very much for reminding me about the attendance code. So the code is, today is Friday, the date is the 17th. Let's set 17. Yeah, that's the code if you're watching. Okay, so let's look at questions. Why in the example in the slide tries repeated twice? Oh yeah, so this was just, you know, like an example. You know, it could have been anything. It could have been a boolean. It could have been a double, a float. Doesn't matter. Yeah. So it was just to just, like, for the sake of the example. Yeah. There's nothing to it. Okay. So yeah. Okay. Thank you very much. Oh yeah. So we are basically out of time. So thank you very much. Enjoy the rest of your day. Remember to, you know, be online on Discord during the practical session, so you can ask questions about your next practical, and so that you can ask the assistants about why you were marked the way you were marked for your previous practicals. Yeah, so very important. Thank you very much.